Colligative properties are solution properties that depend on the number of particles. So not the type of particles, that is not important. It's the number of particles. And when we're talking about these are particles that normally wouldn't evaporate or vaporize off, like alcohol or acetone. So it would be something like sugar or salt that the water could escape, but the salt or the sugar would be left behind. So the salt or the sugar, those are called non-volatile solutes. So again, look, colligative properties are solution properties that depend on the number of particles of what's dissolved in the solution. The first colligative property is vapor pressure lowering. Throughout all these colligative properties, we are going to compare pure water to a solution and look at the number of particles dissolved in that solution. So vapor pressure lowering. So if we were to look at pure water and take the vapor pressure, we would get, in this case, 90 kilopascals. So what's happening here is just at the surface, those molecules that have the most energy, they jostle each other, and with their collisions, they will vaporize. And as they fill the container, they will start to fall back into the surface. And so you will get an equilibrium situation where you will have the same number of particles leaving as coming back. You won't have the same in the liquid versus the gas state, but just the same rate leaving as are coming back. And so when it's in the gaseous form or the vapor form, it will exert a pressure on that container. And in this case, our pressure is 90 kilopascals. And that is for 10 moles of water. And let's compare that to our solution. So now in this solution, we have 1 mole of table sugar dissolved in 9 moles of water, and it will make this solution. When you look at the surface, so this is looking down, you see that the sugar molecules are very large and they take up room on the surface. Because they take up room on the surface, when the water molecules are jostling with each other and escaping from their hydrogen bonding, you find that there's less of a chance for water molecules to escape because the sugar is taking up room. Now, this can be other solutes. So it could be a salt, it could be ethylene glycol, it could be anything that wouldn't normally evaporate off like an alcohol. And so as a result, when you look at the vapor pressure of the container above the solution, we find that our vapor pressure is only 81 kilopascals. Now, there is a way to calculate the vapor pressure over a solution. You should know that the vapor pressure will always be lower for a solution as compared to water. But how you calculate what the new vapor pressure will be, the lowered vapor pressure, is you have to find the mole fraction of the solvent. So this would be the water most likely. And so what you do is you take the moles of the solvent divided by the total moles. So looking at this problem that we have just above, we take the 9 moles divided by the total moles, which is 10, and then you take that mole fraction of water and you multiply it by the original pressure. So 9/10 of 90 is what my new vapor pressure for my solution would be. And so when we multiply this out, we get 81 kilopascals. So it's something that can be calculated, and you can calculate that, but again, you should know that for solutions, the vapor pressure is always lower because there's just less of a chance for the water to escape because the solute is taking up room. So let's address molecules versus ionic compounds that can be dissolved. So when you look at 1 mole of sugar compared to 1 mole of salt or 1 mole of calcium chloride, you find that they will have different number of particles in solution. So even though we add 1 mole to our 9 moles of water, let's say, we end up getting more particles for ionic compounds. So in your homework, I will always tell you if it is molecular or ionic. So what happens with sugar, sugar stays together. Sugar dissolves in water because the sugar molecule can hydrogen bond. When we look at a salt solution, we find that the salt will fall apart. It will fall apart to sodium ions and also chloride ions. Well, these are colligative properties, and colligative properties depend on the number of particles. So for an ionic compound, it will fall apart in water and I will get more particles. So for this one, I will get double the particles compared to the sugar. And so my vapor pressure will be even less. Let's look at this next ionic compound. And this ionic compound, when it falls apart, it will fall apart to calcium ion and 2 chloride ions. Because if you look at the ratio, it's a 1:2 ratio in the compound, CaCl2. So this one will be triple the power of our sugar. So again, our sugar will stay together and it's like it's still just one piece. But all your ionic compounds, they will split and form ions. So positive ions and negative ions, but they're all particles that can be counted to lower the vapor pressure because they take up room on the surface, so there's less of a chance for water of escaping. Let's look at our second colligative property. Again, we're looking at number of particles. And for this is scientifically determined in the laboratory. We're comparing our solution to pure water. We know that pure water will boil at 100 degrees. And let's look at our solution. So if I have 1 mole of sucrose and 1 kilogram of water, notice my units are moles per kilogram. So this is molality, which is a concentration unit that we have previously studied. Notice what happens to our boiling point compared to water. So we find that a 1 molal solution increased my water by 0.512 degrees. So the boiling point increased with the solution. Let's double the amount of sucrose. So doubling the amount of sucrose, my molality now is 2 molal. And notice that I add another 0.512 degrees. And let's triple the solution now. So I have a 3 molal solution. And again, I'm going to increase that boiling point by 0.512. So that we see with each increase in molality, our boiling point goes up even higher. And the reason for this is because as water boils, it needs to break that hydrogen bonding. The sucrose, or whatever the particle it is, it kind of gets in the way. And so water has a hard time escaping and breaking those bonds. And so we end up having a solution that can get well above 100 degrees before it boils. So again, this colligative property is called boiling point elevation. Now remember, for ionic substances, because they dissociate and they form multiple ions or electrolytes, they form more particles. And so this will increase the boiling point even more. So if you look at this problem, what happens to the boiling point if you had a 2 molal solution of calcium chloride? And recall calcium chloride, it is ionic. It will split up into its ions. And I get 3 ions. So you can see that compared to sugar, which is molecular, it just stays together, this calcium chloride, you get triple the bang for your buck, so to speak. So you will triply raise it compared to sugar. Our third colligative property is freezing point lowering or freezing point depression. And again, we're going to look at the molality. So this is done experimentally in the lab. If I take 1 mole of sucrose and 1 kilogram of water, that is a 1 molal solution, I find that my freezing point goes down by 1.86 degrees. Let's go ahead and double the sucrose. Remember, sucrose is a molecular compound. It stays together. And if I double the amount, so I have a 2 molal solution, I find that it will go down even more by increments of negative 1.83. So now my freezing point is negative 3.72. So as the concentration increases, the freezing point decreases. So for ionic substances, remember, they are more powerful because they split into more particles. So I have calcium chloride again, and we find that it separates into 3 ions. Calcium chloride, this is the road salt that we put on our roads in the winter. Why do we use calcium chloride? It's because of this ionic property, this colligative property of lowering the freezing point, and this is by 3 ions compared to table salt, which is just 2 ions. So what this means is when we put it out on our icy roads, it keeps water a liquid longer. So it won't freeze until it's lower, much lower than 0 degrees Celsius. What does a solution do to a phase diagram of water? Well, in the black lines, this is the phase diagram of water. So we have solid, liquid, and gas. Notice that my melting point or my freezing point is depressed or it's lowered. And so that equilibrium line gets shifted over. So the freezing point or the melting point is even lower. And then look at the boiling point. The boiling point gets shifted this way. So I look at it kind of like the letter Y, and I see that my Y shifts wider. So the boiling point increases and my freezing point decreases. Our fourth colligative property is called osmotic pressure. Osmosis is the movement of water through a semi-permeable membrane from a high to a low water concentration. So water will always go from high to low. So let's look at our very first picture right here. So we see that the particles are represented with little dots, and we can see that on the left-hand side, we have a higher water concentration. And so what's going to happen is the water is going to flow through my membrane right here from high water to low water. And so I'm going to end up with equal amounts of percent of water on either side when all is said and done. So this difference right here that it went up, this is called the osmotic pressure. This osmotic pressure is what causes water to go from the ground into the roots of trees, and then those roots grow and they can break sidewalks. And it's all because of this osmotic pressure. And the osmotic pressure is also responsible for water moving up a tree against gravity, along with cohesion and adhesion. They all work together to help water go from the roots of trees all the way to the very top of where its leaves are. Osmotic pressure is important in the human body, in the kidney. As the kidneys clean our blood, a lot of water is taken through them, and we do not want to excrete all our water, and so we want to keep the water in our body. So our kidneys will concentrate the urine so that we get rid of the salts and the waste products that we don't need, but keep the valuable water in our bodies. And so through osmosis, moving from high concentration of water to low concentration of water, we will be able to concentrate that urine and keep the valuable